Okay.
Okay.
Okay. Good morning, everybody, and good afternoon for our invited speaker. Welcome to this second day of the special course at the National Observatory. I am pleased to introduce you the speaker of the next presentation, Dr. Roberto Maiolino. Dr. Maiolino got his PhD in astrophysics by the University of Florence in 1996. And after a few years working in Italy, he moved to England in 2012, where he became professor in experimental astrophysics at the Cavendish Laboratory of the University of Cambridge. In 2019, he also became honorary professor of the University College London, and in 2021, he was appointed to the Royal Society as research professor and later as elected fellow. Also in 2018, he was awarded the Order of Merit of the Italian Republic. Among his research interests, we may find quasars, galactic outflows, gas in the early universe, black holes and AGNs, origin and evolution of dust in galaxies, and obscured supernovae. He has also a leading role in several major projects, some of them already ongoing, like the near-spec spectrograph of the James Webb Telescope and the Clever survey at the ESO VLT, and some of them planned for the near future, like the Moon's near-infrared spectrograph at the VLT, and the project that is the topic of this talk, the high-res spectrograph at the Extremely Large Telescope, recently rebaptized as ArmazoNes High Dispersion Echelle Spectrograph, or ANDES, of which Dr. Maiolino is project scientist. Dr. Maiolino, thank you very much for having accepted our invitation. It is a pleasure to have you here today, and the audience is all yours.
Thank you, and thank you very much for the invitation. And I hope you can now see this full screen, right?
Yes.
And I hope that I don't have problems with the presentation, because I was having a few minutes ago. Just let me know if you don't see the slides changing. All right. Indeed, initially the plan was to talk to you about ANDES, which is indeed the high resolution spectrograph for the Extremely Large Telescope. But then we realized that there was no one talking about more broadly about the Extremely Large Telescope, the ELT. And so I suggested that I also give an overview of the ELT as well, and then I will focus a little bit more on ANDES, all right? So the European ELT is a telescope which will have a diameter the primary mirror of 39 meters. So will be in a few years the largest telescope in the world at optical and infrared near-infrared wavelengths. It's a telescope which is meant essentially to work nearly always at the diffraction limit through a system of adaptive optics, which essentially is built in. The construction started in 2015. And work is underway, and what we just saw is actually an outdated figures. I will show that actually construction is actually progressing very well. And the first slide is expected in 2027, so actually not too far from now. This is an illustration of showing how large the ELT will be with respect to many other telescopes. Okay, so these that you see here are the existing telescopes, the VLT, the LBT, the Keck telescope, the Very Large Telescope, VLT, and so on. And you see that this impressive, step in size, and will be also larger than other planned Extremely Large Telescope which are being, constructed. Just to give you an idea of the size as compared with a football field, this is the size of the primary telescope would take a large fraction of a football field, and the dome essentially would struggle to fit in a stadium. Okay, This illustrates even more dramatically the huge leap in size of the telescope. Historically, you see that there's been a gradual progress in the size of the primary mirrors of the telescopes, and the leap from the current 8-10 meters telescope to the ELT is really huge. So we are talking about a factor of quite a few in size, and therefore, as we'll see, in resolution and sensitivity. So if you want, I will provide a quick overview, but if you want to know more, there is a fantastic site, the European Southern Observatory, which is the agency with the observatory which is developing the telescope, and you can navigate and see actually a lot of more information about the telescope and the science case and the instruments. So the ELT has a primary mirror which is obviously segmented, so it's made of nearly 800 segments, which are of course kept in place to mimic a single, how to say, monolithic mirror. And of course, it would be impossible to make a monolithic mirror of this size. So the concept is that these segments can actually can be kept in place against gravity and other thermal distortion and so on, to always have the shape that you should have for a full monolithic 40-meter telescope. It has actually a 4-mirror design, which I will show in a second, which is required to implement these, as I say, always active adaptive systems in place. And these, the diffraction limited field that it will have will be 10 arcminute, which is quite large for a diffraction limited high resolution telescope. So this is how the light comes into the ELT. So it's been reflected by the primary mirror, then from the secondary M2, a third mirror, and then M4, and then reflected by M5. And M4 is the key mirror, which has, as we'll see, all the actuators that are responsible for the adaptive optics correction of the telescope. So to give an overview of where we are, just to show you that this is not simply science fiction, these are the commissioning of the segments that that you see in this case are how to say have this shape will be of course remodeled, and so this is going very well. So they will have to produce about 800 or more to have spares of these segments, and then these are the secondary mirror and the tertiary mirrors. And you see that are pretty large. Essentially, each of them is the size of, how to say, a medium-sized mirror of a medium-sized telescope that we still are using, of course. So they have a diameter of about 4 meters. And this is how it will look like when it's actually mounted on the structure that will be in charge of holding it and keeping it in place. And the most challenging aspect is the M4, as I mentioned, which is actually a mirror which is made of a shell, thin shell, which has a thickness of about 2 millimeters. And behind that, there are more than 5,000 actuators, which will essentially adapt the shape of the mirror at a frequency of 1 kilohertz to compensate for the atmospheric turbulence. So it's actually a quite challenging piece of technology. It's never been built an adaptive mirror this large, and because it will have a size of more than 2 meters, again with so many actuators. So it's a really cutting edge piece of technology. This is in terms of overall size, how the ELT looks compared, for instance, with the Colosseum, if you have happened to visit the Colosseum, and How it compares also more interestingly with the VLT, so with the Very Large Telescope, which is essentially amongst the largest telescope that we have operative currently, okay, which they have a size of 8 meters. So together with Keck, which have a 10 meter size, are among the largest telescope currently available. And to put it in perspective, this is how one of the very large telescopes would fit on the enlargement platform of the extremely large telescope. So essentially, the extremely large telescope is really massive, huge with respect to the VLT, to the point that indeed they could easily host the VLT on its enlargement platforms. This is the location. So the VLT, so the ELT will is being actually constructed on the Cerro ArmazoNes, which is about 25 kilometers from Cerro Paraná, which is in the Atacama Desert in Chile, where Paraná is already active. So it will be actually in a similar location. And of course, the site has been selected because of course, excellent atmospheric conditions in terms of seeing, and also weather. We want, of course, if you build a telescope like this one, which costs more than €1 billion, you want, of course, to be in a place where you can observe for most of the time and you don't have problems with weather. And also, in particular, the dry place also helps in the infrared, because most of the absorption at infrared wavelengths is due to water vapor, and therefore that helps as well in the how to say, sensitivity. This is a recent picture of the site. As you see, the dome is actually in advanced construction stage, and so all how to say on schedule for the first light in 2027. These are the how to say impressions of the ELT instruments, at least the first and second generation instruments. I will go through some more detailing to each of them. So the Mikado is essentially the primary imager, and Harmony will be an integral field spectrograph. Metis will be the instrument that will work primarily in the mid-infrared, both imaging and spectroscopy. Mosaic is a multi-object spectrometer. And Andes, which I will discuss a little bit more in detail, as I mentioned, will be the high-resolution spectrograph. There will be also PCS, which essentially is an instrument which will implement extreme adaptive optics, which will be mostly used for imaging exoplanets. So just to go a little bit more in details on the individual instruments. So Mikado is, as I mentioned, the primary imager, which works primarily in the near infrared, the red part of the visible, and is aimed at obtaining, how to say, exquisite images with at the diffraction limit of the telescope, and also have different pixel scales going up to nearly 1 arcminute in field of view. It will also actually have a spectroscopic mode with a single slit, and also chronographic imaging, which will be specifically useful for imaging exoplanets. It will be coupled with Morpheo, which will be an additional adaptive optic systems, which will have two deformable mirrors to essentially deliver even higher, how to say, image quality and adaptive optics correction with respect to the standard system of the ELT. And this is very important because you want to fully exploit the size of the telescope in resolution, okay? So because of course the resolution scales linearly with the diameter if you are diffraction limited. But since as you squeeze the PSF you also reduce the amount of background light that you have in your extraction aperture. Actually, sensitivity scales actually with the fourth power of the diameter. So actually, you are much faster in obtaining the desired sensitivity with a larger telescope if you manage to achieve a fully diffraction limited telescope. So you have, therefore, with the ELT, a big step in terms of big leap in terms of angular resolution, and an even larger leap in terms of sensitivity. Okay. You will need also assistance from laser guide stars. That is a system that creates artificial stars in the upper layers of the atmospheres. And by doing so, you essentially ensure that you can essentially observe over a large fraction of the sky. Because if you only rely on, natural stars, you don't have in some areas of the sky enough of them to use as reference point sources to correct the wavefront sensor, to correct the turbulence in the atmospheres, which is in the lower layer of the atmospheres. Instead, by essentially using the laser guide stars, you can have artificial stars, which are always bright enough for the adaptive optic systems to be a reference and deliver an optimal adaptive optics correction of the turbulence across essentially most of the areas of the sky. This is how the image quality and sensitivity will improve with respect to what is feasible currently. So this is an image of a star cluster in scene limited mode. This is what HST can deliver on the same image. This is what you can obtain with the VLT with adaptive optics, so the diffraction limit, and this is what you will get with the ELT. So the leap in sensitivity, in not only in resolution, which you see the image is far sharper, but also in sensitivity is huge, because you not only can get the neater details, but you can detect much fainter stars than, for instance, with the VLT. Okay, so the new capability of the ELT will be quite dramatic, both in resolution and sensitivity. Keep going in terms of for what concerns the instrumentation. Harmony, as I mentioned, is an integral field spectrograph, so essentially can provide a spectrum across a field of view on the sky. So it will deliver cubes where you have both imaging information and spectroscopic information on the third axis. And the wavelength range is still being discussed, but we'll cover from the optical, from the visible to the K band, so around 2.5 micron. And will work both diffraction limited and C limit assisted again with the adaptive optics and with a broad range of spectral resolution from about 300 to 20,000. METIS, as I mentioned, will be the only, for the moment, mid-infrared instrument of the ELT. Will operate from about 3 micron to 13 micron, and will be used both at will essentially provide will be both an imager and a spectrograph, and various resolutions. Mosaic will be the multi-object spectrograph at the ELT, and essentially will be capable of delivering spectra in the visible and in the non-thermal part of the near-infrared bands, which is essentially up to about 1.8 micron. And will be capable of providing simultaneously spectra of 100 or 200 objects simultaneously, but we'll also have a mode where you will have a multiple IFUs, where you have essentially bundles of fibers, which will obtain the three-dimensional, again, integral field spectra of about 8 to 10 objects simultaneously. Okay, and even also here it's will have a different range of spectral resolution. And then there is Andes that, as it was mentioned, of which I'm the project scientist, which is the high resolution spectrograph for the ELT, and the spectral resolution will be about 100,000 or slightly higher, and will provide simultaneously wavelength coverage between 0.4 to 1.85. This is the baseline spectral coverage, but the plan is to possibly expand even to shorter wavelength, about 0.34 micron, and all the way to the K-band, essentially to 2.5 micron. And they will operating both limited and also with the adaptive optics, depending on the science cases. This is essentially a scheme illustrating how will be developed. Essentially will consist actually of 4 spectrographs, each of them optimized for a different wavelength range, and within each spectrograph there will be different arms optimized for a specific wavelength range. And these will be fed by a different set of fibers, which will connect the front end, so the focal plane of the telescope, to the spectrographs. And these fibers will have different properties, different shapes, depending on the science case. So what will happen, for instance, is that in the case of measurement of high accuracy of the spectral profile, for instance, this will be important, for instance, for exoplanets or other science cases that I will mention. There will be a single fiber collecting the light at the telescope, and then the light will be scrambled and distributed across a bundle of fibers, and this will then be distributed on the focal plane of the spectrograph to simulate a sort of a pseudo slit, and this will be dispersed, and you will obtain an Echelle spectrograph for the slit. In another mode, instead, we will plan to have instead the bundle directly at the focal plane of the telescope. In this case, you have essentially distribution of light at the focal plane of the spectrograph, which is reflect how the fibers were illuminated by the seeing. And this is optimal for faint objects because you want to optimize the structure of the spectrum where you have most of the light. And then we'll have a proper IFU, similar to what we have for Harmony and Ricardo, a small one, but which will operate at the diffraction limit with an adaptive optics correction. And in this case, you will actually have a proper, 3D spectroscopy of the small field of view, where you can obtain spectra of each, object falling in each of these fibers. And this will be particularly useful for, again, exoplanets, as I will mention, and protoplanetary disks, for instance, or for imaging the gas around intermediate mass black holes, for instance. This is a simulation of the spectrum that will be essentially, so each of these 2D spectra results from essentially redistributing the fibers in the focal plane of the spectrograph and then being dispersed in wavelength. And you see that there will be actually 2 fibers, one on the targets and one on the sky, to sample the sky. And you will also have, you see all of these dots, these will be fibers which will instead be fed by calibrators, which can be a laser comb or a Fabry-Perot spectrum, or a combination of the two. And this provides a very accurate positioning of a large number of wavelengths. And this will be taken simultaneously with the scientific spectra, and will provide a very accurate wavelength calibration, which is very important for some specific science experiments. So this will be the spectrum that we will obtain by extracting the spectra along these calibrator lines, while this is essentially the science spectrum that you may expect from, for instance, a star or a quasar. So this is how Andis will look at the telescope, more or less. So you will have one divisible spectrograph that will be sitting on the Schmidt platform, while for the infrared spectrograph, at least out to 1.8 micron, it can stay essentially sit in the Coude room, because the fibers in this case can be very long, because the losses along the fibers are very small, and so in this way you gain weight and avoid too much weight and volume on the Schmidt platform. And this is just an organizational chart, which is interesting because it shows how many countries are participating into this project, and particularly, as you see, also Brazil is an important partner of the collaboration. And so I think it's nice to illustrate how that Brazil is very active in this instrument. It is not, I think, the only instrument or system in which Brazil is active. This illustrates the resolving power as a function of wavelength, and you see that all the various instruments essentially sample very nicely most of this plane in terms of wavelength coverage and different spectral resolution. Of course, with Andis and Metis providing the highest resolution, but Mosaic and Harmony providing also lower resolution but of course enabling more other capabilities, such as integral field spectroscopy, as I mentioned, on relatively large field of view, and Wood-George spectroscopy. And this instead is the spectral resolution spatial resolution, okay, and as a function of field of view. And again, here you can have excellent spatial resolution, for example, Mikado, and across relatively, and then also span relatively large field of view, especially with Mosaic. In this case, it's not with Mosaic, is the field of view of that you will obtain is essentially the path of field of view where you can essentially position the various fibers, which is essentially the full corrected field of view available for the ELT. Now, okay, so maybe after this overview of the technical properties and capabilities of the ELT, you may wonder now why we are developing this gigantic telescope with these complex instruments. So what are the science cases? I don't have time to illustrate the huge variety of science cases of the Stimulus telescope, because there are several of them. Is how to say, a facility for the very broad community with a lot of extremely interesting science cases. I will focus on just a few of them, but I would be glad to answer to questions if you want to ask about more science cases. Although, of course, I'm more familiar with the science case for Andis, but I also have some visibility on the other instruments. So one obvious, how to say, very hot science case are exoplanets, and the very high angular resolution provided by the ELT and the diffraction limit is to directly detect and image exoplanets. So this is one system that has been observed with Sphere, and this simulation with Mikado, what can be done with Mikado. And you see that you can easily, of course, detect very nicely the exoplanets already detected by a Sphere at the VLT with thanks to the higher resolution of Mikado and the ELT. But as you see, within this simulation, they have located additional planets at much closer to the star, and you see you can detect fairly easily also exoplanets which are as close as a few astronomical units from the star. So you are essentially starting to probe to image directly exoplanets which are very nearby to the star, so much closer with respect to what has been obtained by current and past facilities. Of course, the goal is to push the detection of exoplanets closer and closer, and to probe possibly rogue exoplanets such as Earth or super Earths in the habitable zone. That is the zone where essentially the distance from the stars where water can survive in liquid form, so not too hot and not too cold, okay? And typically this implies often also looking at dwarf stars, dwarf red stars, because these tend to have the habitable zone closer, and this has some advantages in terms of techniques that I will illustrate later on. So, but more interesting, the important, I think one of the most interesting cases for the ELT, and particularly around this, is tracing the atmospheres and detecting and characterizing the atmosphere of exoplanets. And this can be done in two main ways. One is through transit spectroscopy, so wait for, in cases where exoplanets pass in front of their star, and in this case, the light of the star is being filtered by the atmospheres, and you get the imprint of the various molecules associated with the atmosphere of the exoplanets, okay? And so you do a differential measurement from when the star is in front of the star and when instead is out. And the ELT, and particularly Andes, has the capability of doing this with, and especially in rocky planets. That's the main goal, because this is, of course, already been done, but mostly for Jupiter-like or Neptune-size exoplanets. And of course, the ultimate goal is to detect and characterize atmospheres of exoplanets similar to the Earth. And of course, the ultimate goal would be the detection of biosignatures, which I think everyone agrees would be a fantastic discovery. Okay. The other technique is to explore the exoplanet atmospheres in reflection. So when the exoplanets is instead facing us and getting the light reflected from the sun, you see on top of the on top of the spectrum from the star, you get also the feature associated with the light reflected by the exoplanets and passing twice through the exoplanet atmosphere. Okay, with so this can be done by resolving spectroscopically the features of the exoplanets due to its motion around the star, but you can also combine these with adaptive optics, and so both resolving spatially and spectroscopically exoplanets. So combining these two techniques, so high spectral resolution and high spectral resolution, you have a multiplicative effect where you can characterize even fainter the atmospheres of even fainter exoplanets. Okay. And this is indeed one of the, so combine these two techniques are the primary goals in terms of exoplanets of Andes. So detect the atmospheres of exoplanet both in transmitted light and in reflected light, in this case with adaptive optics. And here you see some numbers where about how feasible is this. And you see that, for instance, it is possible to detect the molecular oxygen in Proxima B, which is one of the closest exoplanets, in 70 hours, which is a lot, but still feasible. This is the cross correlation signal to detect, to find the signature of the molecules. And in the absorption, you see various possible molecules of water and carbon dioxide and molecular oxygen that you can see in another exoplanet, in TRAPPIST 1 and 2. Sorry, this still has HIRES as a name, but as it was mentioned, this is the former name of the Andes, now has been renamed, I think, since last summer as ArmazoNes. The other science case for the ELT, for the Andes and the ELT and Andes in particular, is to characterize the extremely metal-poor stars in the halo and identify those who might be actually have the chemical fingerprint of the chemical production of the first population of stars. It's called population 3 stars. The supernova produced by the resulting from population 3 stars, so the first stars formed in the universe, have a very, how to say, characteristic part in terms of chemical enrichment. And so the hope is that with Andes will be possible to characterize the chemical composition of the atmospheres of these stars and determine whether of these old and very metal-poor stars, and determine whether they actually could have formed from the explosions of the first generation of stars in the early universe. The other goal is, of course, to go and explore directly galaxies in the early universe. One of these is to characterize and understand the what are the the seeds of the massive galaxies in which we see in the local universe, which resulted from the build-up and merging of lower mass galaxies at high redshift. And here we will exploit the far superior angular resolution and sensitivity of the ELT, especially with instruments like Mikado, which will be even superior than instruments like the NIRCam and the JWST. This comparison of a galaxy, how you can see it with NIRCam, which is a fantastic instrument, of course, but with Mikado, you will have a resolution which will be something like 5 or more times better. So you can actually distinguish very well the spiral arms, the bulge, and so on. So this will be it's very exciting science that will be done by the ELT. You will, of course, want to push the frontier to the earliest galaxies, the first galaxies that formed in the early universe. Now, as you have seen, there's been a lot of claims of very high redshift galaxies from the James Webb Space Telescope. And the frontier there is, of course, to characterize these very first galaxies in terms of morphology structure. And this is an example of how the ELT can very nicely, how to say, resolve the structure of very high redshift galaxies in their composition and even the presence of globular clusters and so on. In terms of understanding the distribution of matter and in the galaxies and the intergalactic medium, this also will be another area where the ELT will be extremely powerful. Indeed, a large fraction of the matter, especially at high redshift, is in structures which are distributed between galaxies and in the outskirts of galaxies, in the circumgalactic and intergalactic medium. And the way to probe that, which this kind of matter emits very little, and so is not detectable really in an emission, but you can probe that in absorption by having background sources and seeing the absorption of intervening system, intervening matter, clumps of matters, both in absorption in the Lyman alpha system, but also in possibly in the metal lines if these have been enriched. And this has been, of course, done a lot in the past with the current telescopes. But what will be the novelty, the big novelty of the ELT is that this has been done until now by using a relatively bright background source such as quasars and GRB, because you need enough flux to detect these features. But what will be possible with the ELT is that you can use the sensitivity will be high enough that you can use the galaxy themselves as background sources. And if you do so, you have actually at that point a lot of line of sights that you can, with which you can probe this intergalactic medium and circumgalactic medium. Okay, with the quasars and GRB, you can probe only one, as I say, line of sight every, I don't know, few square degrees, or at least. And while with the galaxy, you can actually have multiple line of sights. And in this way, you can do the so-called tomography of the intergalactic medium and circumgalactic medium. Okay. And therefore reconstruct how the matter is distributed on relatively small scales, and of course compare with simulation to constrain models of formation and evolution of the cosmic structures. With the same technique, of course, you can explore in detail, especially by targeting the highest redshift quasars. You can explore the absorption features in metal lines. And at high resolution, this will provide, especially by using very wide wavelength range, can provide a detailed description of the chemical enrichment of these primeval systems. Okay, so this is probably the best way to pin down the relative chemical abundances of different chemical elements in these primeval systems. And in this case, the idea is the ultimate goal is to characterize this chemical enrichment in such a way that you can directly determine the chemical enrichment patterns in this early system and see whether it matches what you expect from the chemical enrichment from the first generation of stars, that is the so-called population tree stars. So it's something similar to what I was mentioning when trying to probe the chemical enrichment of metal-poor halo stars in our own galaxy, but in this case, going directly in situ in the early universe and directly probing the chemical enrichment in the very early universe, in the first few million years of life of the universe. And this is an example of how this actually is feasible. This is the case of put at the quasar of a redshift 7 with this magnitude observed for 2 hours. And you can see that these are the absorption signatures of oxygen, and these the simulated absorption of silicon-2 and carbon-2, and how, depending on the relative absorption of these lines, you can distinguish between ordinary supernovae, type 2 supernovae resulting from POP3 explosions, so low mass stars, or POP3 resulting from very stable supernovae, which are supposed to be very massive stars. And this is the same simulation at even higher redshift, where you, of course, for the fainter quasar, and you see that, of course, the signal to noise becomes lower, but you can still distinguish between different scenarios of early enrichment. Okay. And I like this because it illustrates the leap in sensitivity. It shows what you can get in terms of sensitivity to absorption system with current observatories, with current instruments such as X-shooter, the VLT. So this is the model spectrum. Actually, this is the model spectrum, and this is convolved with the resolution of X-shooter, observed with 25 hours of these systems with this magnitude along the line of sight of a redshift 7 quasar. And you see that you barely see any of these features. Instead, with the ELT and Andes in only 5 hours, you clearly detect all of these nice absorption features associated with the oxygen 1, carbon 3, carbon 2, and silicon. So you will really have a huge speed in sensitivity and essentially capability of detecting absorption systems and chemical elements in the early universe with relatively, it will be relatively easy with respect to current facilities. The nice thing of the ELT, in particular Andes, is that we'll explore science cases which go beyond the classical realm of astrophysics, but even will go even in the realm of fundamental physics. For instance, I don't know if you follow this, but there's been an attempt to see whether the fundamental constants of physics change across cosmic time. So, for instance, the fine structure constant of which determines essentially the separation of the multiplets in emission in transition of atomic systems, or the ratio between the mass of the protons and the mass of the electron are constants, which are defined as constants because simply we don't see them vary in our local environment in our laboratories. But actually, there is no physical reason why these should be constants across the cosmic ecosystem. And actually, there are theories associated with the nature of, for instance, dark energy and so on, which predict that these what we call fundamental constants of physics actually may be changing across the cosmic epoch. And one of the goals of Andes, which is still here, here is still called the HIRES, is to constrain these, whether there is a variation of these fundamental constants in the early universe with much higher accuracy than what can be currently done with current facilities. And if should be a detection of a variation of these fundamental constants with redshift, that would be a fantastic result, because it would mean that there is a new physics that we hadn't yet put in our, how to say, laws of physics, and would be a great discovery. So this would be one of the important science cases for Andes and the ELT. The other important science case, which is really challenging even for the Andes and ELT, but within reach, it will be characterizing the acceleration of the universe in real time. And you know that the acceleration of the universe has been clearly demonstrated and led to the Nobel Prizes in 2011. And associated with dark energy, and I don't want to enter now into the detailed description, but the idea with the ELT is to have a completely different approach, and essentially seeing the acceleration of galaxies as a function of time in real time. Okay, so the idea is that if you observe the absorption system along the lines of size of a quasar, and at one epoch, and then you wait for a few years, and we'll see how many years, then because of this acceleration, you will see that this feature moves in time, in real time, and so they should move. You see this effect as I move from one spectrum to another, okay? So these lines move slightly. And if I show you the difference, is really time, okay? And you may wonder how much time is needed for these lines to shift in time. And the time that is needed to get this effect is actually 1 million years. So it's a lot. But actually, with Andes, we have an accuracy and a precision in measuring these absorption systems good enough that by observing a number of quasars, which are observed anyway for other sources across a time scales of 10 or 20 years, you can actually get a good detection of this shift and get a direct measurements of the expansion and acceleration of the universe. So you may say, okay, but this is what is called the redshift drift or Sanders test. It's a famous test that has never been, of course, attempted so far. You may say, okay, but we already know that the universe expands and accelerates, and why do we have to get a further proof through this very challenging method? Well, because this would be the only direct, so non-geometric, depending on which would be model-dependent measurements of the expansion history of the universe. Okay, so it's completely orthogonal and independent of all other geometrical methods. So if what you get in terms of cosmological parameters from this completely orthogonal method with respect to the other methods such as CMB, supernovae, and so on, if you get a different, answer, then that would really imply that you have some new physics that we haven't taken into account. So this is actually a very exciting additional cutting-edge science case for the ELT. And I will stop here, summarizing that, so the ELT will be the largest optical near-infrared telescope, which will excel in both collecting power, therefore sensitivity and angular resolution. Okay, as I've shown only a little bit of what can do in terms of science, because the science cases are really many more. I simply didn't have time to list them all, but it has a lot of additional scientific validity, all of them exciting science cases, and of course with a lot of synergy with other facilities that are already operating or planned in the near future. And keep in mind that, again, the first slide will be in 2020, so we will see some of these science cases being actually being pursued already in a few years. And of course, later in the subsequent years, you will see some of these, many of these science cases that are illustrated being developed and their full capability of the ELT. And I will stop here, and I will be glad to take any questions.
Okay, thank you very much, Roberto. Really wonderful presentation. If you have questions, I ask you to raise your hand. Okay. Simone, go ahead.
Yeah.
Hello, Roberto. Thank you very much for this talk. It's very impressive, really amazing telescope and instruments. My question is, are the raw data and reduced data will be available to the observers, and the pipelines for data reduction are being developed
yes,
within the same project?
Yeah. So well, first the data will be available, yes, to the community. In some cases immediately, in other cases after 1 year or preparatory period. And one of the requirements for the instruments is also to deliver the pipeline, which is essentially is a requirement for the consortia to deliver also this pipeline. In some cases, it will be how to say, a simple science-ready spectrum or image. In other cases, the consortia are talking about and the ISO is encouraging to deliver even higher level products. So, for instance, getting not only, for instance, the spectrum, but the fluxes of the lines or the equivalent widths of the absorption systems and so on. But this is, of course, will be on top of the basic reduction. But yes, this is part of the plan.
Okay, more questions? I have one. I was curious about when you showed this slide about the detection of biosignatures in the atmospheres of exoplanets. I didn't understand why it is necessary for certain molecules, why it is necessary to have much more transits than for others.
Well, it's because it typically depends on how deep is the feature. So if you have a very deep feature, then in a few transits you can already have a clear detection. If it is very faint, shallow features, you need to have multiple transits and so pile up signal to noise to get the level where the combined spectrum in the end have a good signal to noise high enough to detect those absorption features.
And how is it expected to disentangle the signal of the seismology of the atmosphere of the star from?
Yeah, this is so there will be so the nice thing of the exoplanet is that the features essentially move with time, following the at least in reflection spectroscopy, following the movement of the planet. So it has a very, as I say, defined orbital more, I mean,
Yeah, they shift with the orbit.
Yeah.
They
And so
wobble
it can,
with the orbit.
it can therefore cross-correlate with the orbit phase, and so
Mhm.
we align all of this spectrum to while the feature of the stars, of course, are fixed or in
Fixed.
terms of how to say variability. You may have random variation and so on. So that's one of the main techniques. Yeah.
Okay, thank you. More questions? Marcelo?
Roberto, thank you. Thank you for the very nice talk. Just to confirm, which instruments should be probably available just after the first light?
So the first light, in principle, should be will be Mikado and the Harmony and Metis. This would be the sort of first light. Now, which will be of them will be actually the first light depends on how the instruments are how to say evolve with time. But those three should be in the very first line. Having said that, in principle, we would actually like to, and also I think ISO would like to have Andes very soon, because at the beginning, at the very beginning, the obtaining good quality images may not be easy because it's a totally new telescope with these 800 segments, with adaptive optics, with this completely new deformable huge mirror. And so they may actually would like to have an instrument which can work in single-limited mode, such as Andes, and deliver science already without actually needing excellent imaging. So it would be nice to have Andes and the telescope on first light, but that's of course would be it's challenging for the consortium to deliver on such small scales. But maybe one of the models and some of the observing mode can be relatively early. Yeah.
Okay, thank you very much.
Okay, more questions? Well, it seems that people is shy today. Okay. If there are no more questions, then we thank again Dr. Maiolino for this wonderful talk. Thank you very much for your time. And we hope that we could enjoy in the future the advantages of these fantastic instruments.
I hope so. Thank you for the invitation, and it was a pleasure.
Thank you very much to you.
Thank you.
Bye-bye.